Hi, my name is Ethan Tracy, and today I will be presenting CatChatter, a machine learning system that generates 360-degree depth maps from acoustic samples. This work was completed as part of the CSIRO's Vacation Scholarship Program under the supervision of Dr. Navinda Kottache. Our solution builds on the system proposed in the IROS2021 paper BatVision by expanding and refining its capabilities in a number of ways. A good question to ask is why one would even consider using acoustics as a perception medium when other sensing modalities such as camera and lidar exist. While lidar is very accurate, it is no perfect sensor. Lidar units themselves are physically large, expensive, heavy, and relatively power-hungry, all of which are undesirable traits for a sensor on a robotic platform. While cameras are an improvement on many of these fronts, they too are not without fault. Sensors that operate using light, like cameras and lidar, are prone to a number of failure modes. For example, these sensors are unreliable in scenarios where air quality is low, such as in smoke, fog, or dust. They also struggle to detect transparent surfaces such as glass windows and bodies of water. In addition to this, cameras need the scene to be illuminated by some light source. Each of these shortcomings can be addressed by using a sensor suite that works using acoustics rather than light. There are a couple of examples of existing systems that use neural networks to process acoustic information to perform scene reconstruction. The first example comes from nature, where over millions of years, animals such as bats and dolphins have evolved to be able to navigate their environment through a process called echolocation. Echolocation works by emitting a chirp and listening for the echoes from the environment to deduce its geometry. Some humans with limited vision have also been able to learn to perform a similar task, albeit with far less precision. Bats are able to rely on this acoustic information alone to catch thousands of flying insects in a single night in complete darkness. Inspired by this, Christensen and others proposed their system BatVision at ICRO last year. Our application of their hardware can be seen on the right. The system works by emitting a chirp from the front-facing speaker and recording the echoes using two microphones that are placed inside silicon human ear molds. The chirp consists of a 3 millisecond sweeping tone from 20 Hz to 20 kHz. These microphones record the echoes from the environment, and this is then processed using an artificial neural network. The network is given the binaural audio recordings and is trained to predict the depth image generated by the stereo depth camera at the front of the system. Christensen and others were successful in demonstrating that a neural network had the ability to learn the mapping between the two domains. Our contributions consist of two main sections. We first present a number of improvements to the original BatVision system that help the model to generalize on far less data by developing a number of cross-domain specific augmentations. We also rework the model architecture to dramatically reduce the size of the network while improving performance. We then expand the system to allow for 360-degree depth maps using more audio channels. We will first cover our experiments pertaining to the BatVision model. In order to recreate the results seen in BatVision, it was necessary to build a data collection system that can capture the audio and depth image samples that the network is trained on. We use the same Z stereo camera that was used in BatVision to collect our prediction targets and comparable components for the rest of the system. It is important to note that the lavalier microphones that we use are nothing special, with similar specs to what you can expect from just about any off-the-shelf microphones. This system was mounted on an office chair and pushed around the office to build our dataset. During data collection, we were careful to separate our test and train datasets to different parts of the office. This would allow us to easily spot if the network was overfitting. In BatVision, Christensen and others present a number of configurations for the system. They investigated the effect of using raw waveforms compared to spectrograms as the input, as well as experimenting with a number of network architectures. Their best performing model was comprised of a convolutional encoder with two fully connected layers preceding a U-Net generator. They also found that the spectrogram representation of the inputs performed better than waveforms, however this was at the cost of network size. After collecting our data, we first attempted to replicate the results of BatVision by using their same network configuration. We observed the network severely overfitting, most likely due to the significantly smaller dataset and very large network size. Over a number of iterations, we found a number of modifications to the network architecture that helped to mitigate the effects of overfitting, while simultaneously reducing the network size. The input to our network is a 2-channel grayscale spectrogram, with each channel representing the left and right audio channels. During our ablation study, we found that representing the spectrograms as grayscale did not hurt the network's performance while reducing the network size. We also opted to remove the preceding encoder and are left with only the U-Net. The intuition behind removing the encoder was that by encoding the inputs before they reach the U-Net, the residual connections are made less efficient, as they serve the purpose of helping the decoding half of the U-Net quote-unquote remember the locality of the features from the input. In the case of our spectrograms, this spatial dimension of the input is actually temporal and is tightly coupled with distances of the objects that the network has to learn. So by preserving these features from the input with the residual connections, the network is able to better take advantage of these connections. Another change that we made to the architecture is in the discriminator. We have opted to use a conditional patch scan discriminator, which is given both the prediction and the audio as inputs and is tasked with classifying patches of the image as real or fake. With both of these changes, our network now mirrors the popular image-to-image translation network pix-to-pix. Finally, we added dropout to a number of the layers to help mitigate the risk of the network overfitting. Another important part of the work comes from our cross-domain specific augmentations. While there has been a lot of work done in augmentations for tasks such as image classification, our problem is quite unique in the way that we are dealing with two different data domains simultaneously. When applying augmentations, it is vital that they do not remove any data from the input that is needed for the reconstruction. During our experiments, we found two augmentations that help the model learn relationships between the two domains. The first domain-specific augmentation that we use is called trimming. It works by trimming the audio sample by a given amount and then limiting the maximum depth of the target image by the same amount. The top figure shows an example of a sample with this augmentation applied, with the left and right spectrograms in the corners. The second augmentation is called deafening. This augmentation works by deafening one of the audio channels and applying a gradient to the corresponding side of the target image. This should help the model learn the mapping between the two input channels and the locality of the spatial features of the output. At training time, a sample has a 50% chance of being augmented, and if so, then one of these augmentations are applied. After implementing these augmentations, we observed a 7% improvement in our L1 score on the test set. These augmentations not only help the model learn by showing it manually engineered features of the domains, but also allow the model to train for longer without overfitting, as each augmentation creates a new unique sample for the model to learn from. Here's a quick look at the training process. The discriminator is trained on both real and fake batches once per epoch, and the generator is trained using a loss signal from the L1 pixel-wise difference with the target image and the prediction from the discriminator. And here are the results from our model compared against the comparable models from BatVision, as well as the follow-up work from the same authors where they utilized generalized cross-correlation features from the input to assist in the network's predictions. As you can see, we observed both a quantitative and qualitative improvement over BatVision, all while reducing the size of the network from roughly 58 million parameters down to 14 million. The prediction for a number of randomly selected samples from the test set can be seen at the bottom, with the top row being the ground truth and the bottom row being our network's predictions. It is important to note that our training dataset was less than a fifth of the size of BatVision's, where they trained using 39,500 samples while we used only 7,500. This also highlights a problem with comparing our results due to the discrepancy between our datasets. During our experiments, we were struggling to understand why, despite our predictions appearing to closer match our targets, our L1 score was considerably higher than what was reported in BatVision. It turned out that this was most likely caused by our data collection system being mounted higher off of the ground, and as a result, a lot less of the target image was made up of the floor, a surface with a constant angle which the network could reliably score very well on. This suspicion was supported by looking at the L1 score of the mean depth map. The mean depth map can be calculated by getting a pixel-wise mean of the target images from the training set. We can then get an average L1 loss value for this image against the test set. This can give us a pretty good idea of the quote-unquote difficulty of the dataset, as it helps reveal areas of the image which are more static and as a result are easier to learn. It turned out that our mean depth map's L1 score was 72% higher than BatVision's, which helps explain the discrepancy in our observed L1 scores. Inspired by this, we proposed a new metric that takes this mean depth map L1 score into account to help normalize the performance of the model to the difficulty of the dataset. We call this measure the mean percentage loss, or MPL for short. It captures how well the model is able to improve the L1 score over the baseline of the mean depth map. We now move on to CatChatter, the 360-degree expansion of BatVision, where we use lidar instead of stereo cameras to generate the ground truth. The hardware is comprised of the IROS cat pack running lidar-based Wildcat SLAM. 2 additional microphone and ear combos were used to make up a total of 4 audio channels. The ears are positioned symmetrically around the base, facing away from the center. The speaker is mounted facing upwards in the center of the system in order to emit the chirp more omnidirectionally. The system is placed on top of a trolley which can easily be pushed around to collect our dataset. The main challenge in adapting our system to work with 360-degree data comes from actually generating the data in the first place. As we gather the samples, we use Wildcat to generate a point cloud and a time-stamped trajectory. Simultaneously, our data collection script is generating the chirps and recording the audio samples along with a timestamp for each sample. This allows us to, for each sample, find exactly where the system was in the point cloud and render an equirectangular image at that location. We did this using the Unity game engine, which also provides us modeling tools to clean up the point cloud where needed. As you can see from the example on the right, one of the failure modes of traditional visual sensing modalities is rearing its ugly head and leaving us with an inaccurate point cloud by being unable to detect the glass windows of our offices. Acoustics would reveal that there is in fact a surface there, and as a result, training using the point cloud as is would be detrimental, as even if the model was rightfully predicting a surface being there, it would be penalized as it wouldn't match the target image. Thankfully, because we're using Unity to render our point clouds, we have the means to amend these errors in the ground truth. By simply placing a plane over the transparent surfaces in the scene, we are able to quickly and easily create a cleaned up version of the scene without the missing surfaces. We also place planes over the ground and ceiling, as otherwise the point cloud is not always dense enough to show these as solid. This now leaves us with a clean and accurate scene ready to be rendered for training samples. This now brings us to the model architecture of CatChatter. The model is mostly unchanged from our front-facing system, with only a few kernel and stride sizes changed in order to facilitate the larger target images. Of course, the model also takes 4 channels of spectrogram inputs instead of the 2 from the previous model. Both of these minor changes result in a larger model, however this is to be expected as the reconstruction task is made more difficult thanks to the target image containing 4 times the spatial information. The new model contains 40 million parameters, which is still smaller than the original BatVision model. The augmentations that we introduced earlier were also adapted to function the same way for 360-degree depth images and 4 audio channels. And here are some of the results from CatChatter, again with the top row being ground truth and bottom row being our predictions. As you can see, the model is able to capture the general geometry of the scene very well. We also observe the model quote-unquote hallucinating some of the finer details, thanks to the signal from the discriminator overfitting it to the office environment. From these samples, we can also see an example of 2 failure modes from the system. The first failure mode that we observe occurs when there is an object very close to the system. This sample shows this clearly, with the model being unable to see the wall that is very close to it. The second failure mode can be seen in this image, where cluttered and complex scenes can bounce the echoes in a way that makes it difficult to reconstruct. All in all, the system performs very well for single audio-to-depth predictions, however there is still plenty of room for further development. When looking at possible continuations of this work, the area that stands out the most is making the system more usable for real-world application. As previously mentioned, the current system works very well for single-instance audio-to-depth predictions, however it is clear that it is unsuitable for deployment in its current state. This is because of the temporal stability, or lack thereof, between predictions, which would pose too great a challenge for even the most robust SLAM algorithms. We are currently working on a new model that remembers its previous predictions in order to maintain stability between runs. This is especially important for deployment on robotic platforms, where a robot traverses a persistent environment, as we can capture multiple unique sources of the same target to build confidence in our prediction over a series of chirps. It would also be very interesting to see how well the model scales with more data, especially from multiple scene types such as offices, warehouse, caves, and in vegetation. Finally, it would be interesting to assess the effect of using ultrasonic microphones and speakers to closer match how bats perform the task. While our microphones and speakers operated at 20 Hz to 20 kHz, bats often perform echolocation using chirps in the 70 to 200 kHz range, with specialized ear shapes that may be better suited to the task. There is still plenty of work to be done on this topic, and it'll be exciting to see where it goes in the future. Thank you for watching.